All right, so the general title of this section 9.4 says comparison of series. There are two comparison tests, and you give a little, you get a little. So they're both good to use, and they can often be used interchangeably, but sometimes one is a little easier to use than the other one, and it just sort of depends on the context of which one it is at which time. So we're going to take a look first at what's called the direct comparison test, okay? So the direct comparison test says the following. We have a sequence, A sub n, well, A sub n and B sub n, they're both positive, but A sub n is smaller than B sub n for all n, right? So A1 is smaller than B1, and A2 is smaller than B2, or equal to. And the two things that can happen are the following. If B sub n converges, right, that's the bigger series converges, then clearly the smaller series will as well. Does that make sense? The bigger one converges, the smaller one's going to as well. And then the second one says if the smaller one diverges, then clearly the bigger one will diverge as well. Makes sense. Now, that doesn't tell you everything, right? It doesn't tell you that, that sometimes we can have ones where the smaller one converges and the bigger one diverges. We don't have that addressed here. But we do have some pieces addressed here that are sort of very logical. Here's the thing that makes this a hard test. Sometimes it's really hard to make sure that the sequences are always one smaller than the other. That's not always an easy thing to make sure happens. But in order to use this test, that's one of the conditions. You with me? Okay, so let's take a look at an example. We're going to use a direct comparison test to determine the convergence or divergence of the series. So we only have one series given to us, right? So there's only one sequence listed here. It's n squared plus 1 over n cubed minus 3n minus 2. And as you're looking at this, one of the things that you might sort of make note of to yourself right away, because it is sometimes helpful, is what approximately is this series? Well, you look usually at the dominant pieces, right? So the dominant pieces here are these pieces, agreed? Like they are going to eventually overpower everything else that's in the numerator and the denominator respectively. You good with that? Okay, so basically, right, if I'm thinking about like approximately, this is approximately n squared over n cubed. And what is n squared over n cubed? 1 over n. This is approximately 1 over n. Do you remember what happens with the series, the summation of 1 over n? That's the sequence. The sequence goes to 0. The series diverges. It's the weird one. It's harmonic. Or you can use p-series. You guys over here said you liked p-series, right? This is p-series with p equal to 1. So it's specifically the harmonic one, right? But p-series works as well. This thing diverges. So as we're taking a look at this and we're saying, this series that they gave me is pretty close to and almost exactly like something that I know that diverges eventually, then it's probably going to diverge. Does that make sense? Eventually, these two series are negligibly different. And if one of them diverges, we would expect that the other one would as well. Now, we need to make sure that we're really able to get the right ordering of things, right? It said on the previous screen that I need my A sub n to be less than or, it's 0 on the other side, less than or equal to B sub n. And I've just decided that this is approximately 1 over n. I didn't decide it, but I sort of thought about it. I have realized this is approximately 1 over n, and this diverges by the harmonic series, or because it's a harmonic series if you prefer, or you can write p-series if you want, that's fine too. And that means the original one should diverge as well. So if you take a look over here, we're in the second category about divergence. I'm expecting something to happen that diverges, which means, do I want my 1 over n to be A sub n or B sub n?
B sub n.
Ooh, I've heard both of them. Think for a second. I want it to be A sub n. I want this 1 over n business to be A sub n. And I want it to be A sub n because if A sub n diverges, so will B sub n. And my expectation is that these should both diverge because one of them does. Here's the problem. I want to make sure that I have a way to say for sure that I know that my B sub n, that's the original problem that they gave me, really is bigger at every term than A sub n. And I have to be able to justify it. And it can't just be look at the graph. And it can't just be, let me show you a few examples. Let's let a equal to 1, n equal to 1, n equals 2, n equal 3, because it has to work for all of them. Right? It has to be a general statement. So the hard part about using this theorem is actually verifying that I really do have the ordering of my a sub n and b sub n correct. Do you guys get it? Okay, that's the hard part. So how does it work? Well, it works something like this, and it doesn't work for everything, okay? Like, it's not going to work all the time. So sometimes this is harder than others. It will work here. So take a look at this. We're going to take n squared plus 1. This is my sequence b sub n over n cubed minus 3n minus 2. What happens if I just, take off this piece right here? Will the sequence get bigger or will it get smaller? It will get smaller. Why will it get smaller? Well, because I took something out of the numerator, right? You have fewer amount or a smaller amount in the numerator, then the fraction is going to be a smaller fraction. Agreed? Yes.
What'd you do to the denominator?
I just rewrote it funny. Let me fix it. I got busy talking, Preston, and I didn't write it down right. Better? I know, it's true. Okay. Aside from my weird denominator situation, is everything else okay? So we can justify that this makes sense because I made the numerator smaller, so it makes the whole fraction smaller. Now, the next thing I'm going to do is I really want these pieces to go away. So if I take these pieces off, I actually have the fraction that I've been looking for, right? I mean, like that's what I'm shooting for right there. Is it really going to still be bigger? Like smaller than it was before? Am I making it smaller? I am. Why in the world is taking off something negative in the denominator going to make it smaller? I have a larger denominator, and if I divide something by a bigger number, then it's going to be smaller. So if you want to jot yourself down a couple notes, you can make things bigger or smaller, but you have to be careful, right? In order for sure to make something smaller, which is my goal in this, I have to take something positive away from the top or negative away from the bottom. If I were taking something negative away from the top or positive away from the bottom, I cannot guarantee the direction of this inequality, correct? It might still work and it might not. And I can't just make the statement quite so blanket-like. So this is going to be my 1 over n, okay? So this is my b sub n. I said that wrong. This is my a sub n, and I started at my b sub n. So a sub n, which is 1 over n, and b sub n is the original one I had, so n squared plus 1 over n cubed minus 3n minus 2. 0 is less than or equal to a sub n is less than or equal to b sub n, right? We created it to be such. I'll go ahead and write out fully since I've kind of written pieces of it. And the summation from 1 over n from n equals 1. This one starts at 2, so we'll start it at 2, right? It's up here starting at 2. So we'll start this one at 2 as well. N equal 2 to infinity. Diverges. You can say by the harmonic series or by the piece series. So, by the divergence test, divergence test is not what I meant to say. The direct comparison test is what I meant to say. By the direct comparison test, the summation of n squared plus 1 over n cubed minus 3n minus 2 from n equal to 2 to infinity will also diverge. So notice a few things that have to be here. Number one, you have to be able to justify that you've got the ordering of a sub n and b sub n correct. Has to be able to be justified in a series of inequalities or in some other fashion. You have to justify that you've got that order right. Secondly, you've got to actually state how you know that whichever one you're comparing it to really does diverge or converge. maybe you'll find that it really converges, and it really converges by the p-series, or it really converges by the geometric series, right? You've got to actually say it converges and this is how I know, or it diverges and this is how I know. And then you have to say by the direct comparison test, this thing will also do the same thing. It will also converge or it will also diverge. So you're going to cite two different series theorems when you're doing these tests. Does that make sense? Okay. Now, it kind of seems like, should it really even matter if I for sure get this limit, like that the b sub n and the a sub n in the right order? I mean, does it really matter? Because even if it were slightly bigger or slightly smaller, I mean, if it's negligibly different, right? If it's different by, if this numerator had said -1 instead of +1, I mean, it would still diverge, right? Like just changing that +1 to a -1 really shouldn't affect whether this thing converges or diverges. Y'all with me? But if it said -1, it'd be a lot harder to make sure I get this ordering right and be able to use this test. So in a case like that, this other test is a little bit more helpful. So this is the limit comparison test instead of the direct comparison test. So in this case, if a sub n is positive, and the limit as n goes to infinity of a sub n over b sub n is equal to L, where L is finite and it's greater than 0. So L needs to be a number, right? It has to be a 7 or 447, right? It needs to be a number. The number has to be positive. Then if the summation from n equal 1 to infinity of a sub n, then the summation from n equal 1 to infinity of a sub n and the summation from n equal 1 to infinity of b sub n either both converge or they both diverge. They're going to do the same thing. So if I can get this sequence to match close enough, which is what I did in the last one, I said, I mean, basically this extra stuff at the end of the numerator and the denominator, they don't really matter. They don't greatly affect this as n goes to infinity. And if I'm able to take those ratios and I'm able to actually divide them and get a constant, right, a number, it's not 0, then they should both do the same thing. So I don't have to worry so much in this case about getting the ordering of things right like I did before, but the drawback is I have to do a limiting process that I didn't have to do before. So you give a little, you get a little, right? We don't have to worry about the ordering, but now we have to do a limit. So here's a good example of one where the direct comparison test would be very challenging to do. So take a look at this. What should this be approximately? Can you tell? It should be 1 over n squared. It's about 1 over n squared. The parts that are actually dominating are the highest degreed pieces. That's n cubed over n to the 5th. And if I simplify those, this is basically the function, like the sequence rather, 1 over n squared. What does 1 over n squared do as a series?
Converge.
This one converges. How come?
Because p is greater than
Yeah, p series of p is greater than 1. This series will converge. So my expectation is the series that they gave me to begin with, it also should do the same thing because they're negligibly different. Okay, does everybody make sense of that? The problem is that if I were trying to set up an inequality like I did on the previous one, it's not so friendly. The numerator's fine. I can take some extra pieces off the numerator and for sure make things smaller or bigger, right? But what happens in the denominator doesn't actually help. So if I take extra stuff off the numerator, it makes it smaller. What happens if I take the extra stuff at the end off the denominator? It makes it bigger. And when one of them makes it one thing and the opposite happens on the denominator, the numerator, that's very difficult to establish a relationship that says greater than or less than. Because one of them is becoming bigger and the other one's becoming smaller. Does that make sense? So the limit comparison test is a more reasonable way to approach this problem, but it's a little bit trickier because I have to do the limit part of it that I didn't have to do before. So the first thing is that we've established what we expect a sub n to be. A sub n is pretty much 1 over n squared, right? That's what my expectation is, right? It's 1 over n squared. B sub n is the one that they gave me originally. This is B sub n. So we're going to actually figure out what happens when we do the limit. Okay, Okay, so this was like step one, is establishing what a sub n is. I need the limit as n goes to infinity. And if you take a look over here, it says I need either a sub n over b sub n, or I could do b sub n over a sub n. It doesn't really matter, right? Put one on top, put one on bottom. I tend to put the messier one on top. It just looks a little bit nicer in the end. So I'm going to put the original one that they gave me on top. So this is n cubed plus 2n plus 3 over n to the fifth plus 2n plus 4. And it's over 1 over n squared. Okay, so I'm finding the limit of the ratio. I don't like fractions inside of fractions, and neither do you. It doesn't make things easy to work with. What would we do to eliminate the fractions inside of fractions here? Yeah, we're just going to flip it, right? Multiply by the reciprocal. So this is the same thing as the limit as n goes to infinity. We have the same thing that we had on top. Oops, I didn't mean to cut. I meant to copy. Let's try that again. And instead I would be multiplying it by n squared, or n squared over 1 if you prefer. All right, so if I take that and I multiply that through, then I've got the limit as n goes to infinity of n to the fifth plus 2n cubed plus 3n squared over n to the fifth plus 2n plus 4. Okay? I've got a ratio here now that's the n to the fifth over n to the fifth. This is going to be 1 eventually, right? Y'all with me on that? Okay? And the way that we established this, and we did it back in Calc 1 for those of you who had Calc 1 with me as well, is that we multiply by the highest exponent on top and bottom as a fraction. So the highest exponent is a power 5, so we're going to multiply by 1 over n to the fifth. And when we do that, that's going to give us a lot of mess for the moment, but that's okay. We'll get to simplify it very quickly. So I have 1 plus 2 over n squared plus 3 over n cubed over 1 plus 2 over n squared plus 4 over n cubed. And all of these little pieces that have a number, like a constant over n squared, n cubed, whatever they are, if I take their limit as n goes to infinity, these all tend to 0. And we did talk about this in section 9.1 when we were looking at sequences. So this gives me 1, right? I've got 1 on top, I have 1 on bottom. This limit is 1. That's what I need, right? I need a limit that's finite and it's positive. And I have it. The limit is finite, the limit is positive. Now, it's probably worth noting that if there had been a constant in front of like the n cubed, like it didn't say n cubed, it said like 3n cubed. Okay, that's fine. All that's going to happen down here at the end is I'm going to get a 3 right here. Right at the very beginning, I'm going to get a limit of 3. It's fine to have a limit of 3. There's no problem with me having a limit of 3. Okay, I'm allowed to do that. I just need to have a constant, which 3 would be, that's positive, and 3 is. So the number doesn't matter. So as we're taking a look at this, whereas like over here, it would have, right? If I was trying to establish the relationship over here, and there was a 3 on top, I'd need to make sure that the comparison thing that I picked had a 3 in it here as well. Over here, I don't need to worry about the constants that are different. I really only have to worry about the coefficient, or about the exponents being the same, making sure those match. All right, so this was equal to 0, or equal to 1, which is greater than 0. Hang on. Let me shift this over just a minute. That's what I want to say. And, hang on. Come on. The last thing to do is to write out the pieces of everything we've just found, okay? So over here, we work hard to get things in the right order as our sort of preliminary work. Over here, we work hard to make sure that we've got the limit value that satisfies the criteria. Constant greater than greater than 0. And we're actually going to write that down then. So this is sort of our conclusion. So the series, what was the number it started at? 6. The summation from n equals 6 to infinity of n cubed plus 2n plus 3 over n to the fifth plus 2n plus 4 converges by the limit comparison test? Because the limit as n goes to infinity of, and it's this value, n cubed plus 2n plus 3 over n to the fifth plus 2n plus 4 divided by 1 over n squared equals 1, which is greater than 0. And the summation from n equal to 6 to infinity of 1 over n squared converges by the p-series test. And you could flip this around. You could start by saying this thing converges by the p-series test. This limit is going to be equal to 1, which is greater than 0. Therefore, this happens. So the ordering of how we've written that is not so important, but one fact hinges on the other one. Any questions on either of those two tests?